Hello, everybody. I'm Niharika Gogoi from Friedrich-Alexander-Universität, Germany. And today I will deliver my talk on simultaneous step counting and energy harvesting from piezoelectric-based embedded machines. So we are all amazed by sensor technology, and that's why we are here together. But in this talk, I will deliver about wearable devices, and that's basically concerning the problem with wearable devices or any sensor applications. So what is the problem here? So most wearables are operated by batteries. Batteries have a specific lifetime and needs replacement. And these replaced batteries are dumped to the environment. And as a matter of fact, all batteries contain toxic materials, which is very unfriendly to the environment. So therefore, it's very important for us to either shift the energy source from the battery to ambient energy harvesting, or otherwise improving the battery ingredients. So that was the motivation of my talk, and I'll deliver about my area of interest and our investigation about two unaddressed concerns. And here I'll also discuss about two types of circuits and the circuit analysis and the conclusion. And I would also like to tell that I don't synthesize piezoelectric materials. I only work on the circuit part, basically the rectifier circuit, or you can say the interface circuit, and also in the data acquisition circuitry. So my area of interest is smart shoes and do the simultaneous step counting and energy harvesting from the piezoelectric disc. Why shoes? Because shoe is something that everybody wears it. Whether you're sick, old, healthy, young, athlete, anybody wears it. And the next thing is that when you think about harvesting energy from any human movements, shoe is something that, or your feet is something that gets the most amount of pressure. So that's why it provides a very good platform for wearable devices. So before I talk about my concerns in this study, I just want to show you the system architecture of the whole design. So you can see that I have put 5 piezo elements at different positions of the feet. And then you can see I have drawn with 2 different colors of arrows. One is the teal color, which is telling us about the sensing direction. And the other one is the blue color, which is telling about the energy harvesting. So I use 1 piezo for sensing and other for, the total 5 for energy harvesting. So what is the first concern that I'm addressing? First thing is that can we do sensing and energy harvesting from the same piezoelectric element while walking or not? And the second one is that I'm comparing 2 types of rectifier circuit. One is the standard full bridge rectifier circuit, which is very common. And the other one is self-powered synchronous electric charge extraction, or SPSEC, which I'll shortly take it frequently for gate-based energy applications. Okay. Now briefly about the circuit. So the first one is the standard circuit. I hope everybody is aware of it. But the second one is the basic SECE or SPSECE. So how does it work is that whenever there is a maximum peak, the switch is turned on and the energy is transferred to the transformer. But you have to turn on the switch at the right time. For that, I have used electronic breakers. So the electronic breaker is composed of, I can show it. It's composed of so here it will not detect the maximum charge source, and when the voltage is going down, this acts as a comparator and this switch is turned on. Then the whole starts transforming. Yes. So one important thing that I would like to say is that piezoelectric energy harvesting, there are widely studied, there are a lot of papers, but the point is that people always consider sinusoidal wave and also at a very high frequency. high in the sense 50 hertz or 100 hertz, something like that. But our gate signal looks something like that when you're walking. So it's definitely neither symmetric nor it's very high frequency also. So this is also one of the reasons why I did this comparative study to look at like whether, because in the existing literature, they always say that SPSEC or SPSSHI outperforms the standard SCH circuit. But does that really happen when we try to harvest energy from human movements? Or for any ambient energy harvesting, it's not so easy to get 30 hertz around the environment. It's always around 1 or 2 hertz. So this is my circuit analysis. So you can see that there are quite a few components in the SPSEC. So basically, first, I try to decide the right component for the envelope detector. So here, what I do is that I fix only one piezo at position 3, and then I do the circuit analysis and try to walk around. At that point, I see that the best envelope components are at around 100 nanofarad and without any envelope resistor. And then I try to see the load components. For the load components, I see that the best result is for load capacitor 4.7 microfarad and 330 kilo ohm. So based on this components, I arrange all the 5 piezos parallelly. And then I do what I showed in the initial system architecture. So here you can see that I have 4 circuits. So this is basically telling you about the step that you're getting from this piezo. And this is the EH on, which is a pin in LTC331. So what is LTC331? This is a DC converter, and the rectified voltage that's coming from here, it's regulating it and it's powering the MSP 430. And then we are trying to get the sensing data from this piezo. So, and EHON is a pin in LTC331. And in this pin, what happens is that it tells us about which input is used to operate the MSP. So if it's high, it means the energy harvesting circuit is on. And if it's low, it means the low, or then it means that battery is in use. However, in this part, and here you can see the output of LTC331. It needs certain number of steps to get the right voltage. And for the battery, I have set it for 3.7 volt. And for the output of the LTC33, which was set for 2.8 volt. Now, after using all the piezos in parallel together, and then I tried to do calculate the total power around that. So here you can see that SEEH is giving us more power than SPSECE, whereas in the most existing literature, the opposite was true. So basically, what I would also like to refer is that the efficiency of any harvesting circuit definitely depends on the type of input and the type of material, obviously, but also the frequency at which it is working on. So it's not like a standard rule that SPSEC is always going to perform better than SEH. So this is the total summary of the circuit analysis. So if you see the number of steps, of course, SEH is getting charged faster or achieving the desired voltage faster than SPCE. Also, the charging currents are low for SPSECE. So with that, I conclude my talk, and you can see that we could do simultaneous sensing and energy harvesting together, which is possible. Then also we see that SEH requires less voltage to achieve the desired less steps to achieve the desired voltage, and also generates more average output power when we arrange it in parallelly. But for SPSEC, we see that here this current is low. So discharging current when the person is standing, because we have a transformer isolation and also this diode. So the discharging current is less, and it's less than the SEH. And in the next step, like this is quite an old work, like before I submitted into the conference. And after that, we have also tried with Bluetooth transmission and definitely to lower the dependency on the batteries. And we are also trying to do with multimodal sensors, especially using accelerometers to do the gyre monitoring, and then do the harvesting by piezoelectric energy harvesting. With that, I conclude my talk, and I'm happy to answer any questions.